Our next topic then is going to be about solutions. And solutions, remember, we do have solutions where we have very, very tiny molecular sizes, and they're able to mix together to where we can't even tell the different components of them, as opposed to like a colloid, where you have two separate phases. Particles tend to be larger molecules. It's positive for the Tyndall effect. So if you looked out like on a morning where it's kind of hazy, you can see the rays of the sun coming through. That's the Tyndall effect. Or if you're in the fog and you put your lights on bright and it's internally reflecting off of those um, particles, that's the Tyndall effect. Suspensions then, you have the ability to filter out parts. They settle over time. So when you had like sand and water, for example, the sand's going to sink to the bottom. When we're dealing with solutions, though, we have very tiny molecular sizes. They're able to get mixed in thoroughly, and you can't really tell the components one from another. You can have solutions that are gases, liquids, or solids, or a combination of these. Um, for example, alloys that we talked about earlier in this unit and last unit, those are mixtures or solutions essentially of solids, of metals. So they'll heat the metals up, get them into a liquid state, and then they will mix them together and then cool them back down into a solid state. And then you could have gases in liquids like your pop, for example, or you could have solids in liquids like salt in water. So there's various ways that you can get these mixtures to occur. So the particle size distinction means that a mixture can be, it can appear homogeneous, and it looks like it's just one thing. So naked eye colloid also, it looks homogeneous, but if you really magnified it and got it down there, you would say that it was still heterogeneous because the parts are still, they're large and you're able to separate them more on a more magnified scale, but you're still able to do it. So liquid solutions, solute again can be a gas like a CO2 in your pop, or it could be a liquid, or it could be a solid. So we talked about that a couple slides ago. Liquid solutions by definition can be separated into their components because remember, solutions are a physical change. When we go through a physical change, we can still get our components back. And so one of the ways to do that is through chromatography. And we looked at that lab back earlier when we were looking at IMFs, and we used that as a way to separate material. So the chromatography, again, if you kind of look back at that, in most common applications, it's usually paper chromatography. You might have done a lab like this when you were in elementary school, where they put Skittles on a wet them just a little bit, put them on a coffee filter, and then put it in water, and then over time the dye from the Skittle moved up that paper and kind of separated. So it's kind of a neat lab that they do when they're talking about science in some of the younger grades. Um, when we do it in here, we're looking at it in terms of those intermolecular forces, the two phases, see which one, that has weaker intermolecular forces. If the component of the mixture then has a high affinity for the mobile phase, then it's going to move up the paper. If it has the more of an affinity for the paper, then it's not going to travel as far. And you saw that when we did the chromatography lab. So and then you look at that distance that it traveled. So here's kind of an example. This is a very common type of question that you will see on the AP exam. You look at the distance that's traveled. So if we looked at these two dyes, this one would have more of an affinity for the solvent that was in it, and this one would have, and especially this one would have more of an affinity for the paper. So then you have to look at what the solvent's made out of, and you also have to look at what the paper's made out of and determine if those are polar bonds, non-polar bonds, and which ones the solvent traveled better in. So this is kind of what one of those chromatography examples would look like. Distillation is another example of this where we separate based on the various boiling points. So here we have a liquid mixture, and we're taking advantage of the differing boiling points of the different components, and different things will boil at a different temperature. So ethanol, for example, that'll boil at a much lower temperature than water. So if you had ethanol and water mixed together and you wanted to drive off and capture the ethanol, you would heat that up. You could heat it up to like 78 degrees. The ethanol would come off, but water doesn't boil at that temperature, so the water would be left behind. This is essentially what they do in petroleum industry when they're trying to break apart crude oil. So crude oil comes in. It has a bunch of different components to it, and they'll heat it up based on the boiling point and start pulling off at the refinery different things that boil at different temperatures until they're able to get everything driven off that they want to take care of. So this is what one of those distillation apparatus looks like. You have a heat here. You'd have a mixture. Let's say that this is our ethanol and our water mixed in here, and we want to get just the ethanol off. So they'll heat it up to about 78 degrees. We would hope that they wouldn't use wood here because it's probably not a good idea, but in this drawing, that's what they chose to use. So they're heating that up. The ethanol will be driven off. Then they have this tube here. It's surrounded by another tube. They don't mix together, but it's just surrounded by that. And they've got cooler water coming in here so that this ends up condensing the gas back into a liquid, and then they're able to get the pure ethanol over on the side. So just like I said, takes advantage of those two different boiling points. So in Unit 1, we saw that the composition of a solution can be expressed in terms of moles per unit per liter. So that's called molarity. We also learned about that last year in chemistry. Relatively low molarity solutions, you don't have a lot of solute particles. And so we kind of think of those as kind of being weak. So if you made like Kool-Aid and you put in twice the amount of water than you should have, that would have a relatively low molarity, as opposed to making Kool-Aid and putting in half the water that you're supposed to. That would have a high molarity comparatively. So when we look at solutions and we're creating these, you need to you add water to it, the more concentrated ones, and you can figure that out. So we calculate the number of moles present in the final diluted solution and the moles, and we equal that to the concentration and the volume. So we calculate the volume of the starting. More concentrated solution, again, supplies the number of moles by applying the moles. And then the volume of the water that must be added to the concentrated solution is simply the difference between those. So here's kind of an example of what we're talking about. In order to calculate the volume of water that must be added to a 2 liters of 3 molar potassium hydroxide from stock solution. Stock solution has a concentration of 8 molar. So if we know that our final solution, we want to have 2 liters of it and we want it to be 3 moles, then we can calculate that out by using this formula to figure that out. So you can pause the video and kind of take advantage of looking this over. All right, practical terms, we use graduated glassware. Typically volumetric flasks are what we use for this. Graduated glass pipettes, burettes. We'll be using these when we get into doing our Beers Law Lab in another few days. And we add approximately 1 liter of the distilled deionized water to a 2 liter flask. Then you add in your concentrated solution, and then you continue to fill it up until you get to the 2 liter mark. So this is what a volumetric flask looks like. It has 1 marking on it, and that's it. That's the only thing it has, as opposed to like a burette or a graduated cylinder or something of that nature. These are made to only measure a certain volume. So we have a variety of these in the back storeroom. We have anywhere from, I think I might have a 2 liter. Most of the time we just use the 1 liter. We have 50 milliliters. We've got we've got little bitty 25 milliliters. So we have these, and this is what you're going to be doing your dilution in, is a volumetric flask. So what you end up doing is you have to dispense out using a burette typically. Sometimes we use graduated cylinders if we're, you know, kind of cheating, because these are a lot of work to clean up. But people oftentimes will want to use those when they're working with the dispensing it. So the burette is going to give you a very, very accurate measurement of volume. It's probably the most accurate that we have available to us. So if you have, oftentimes on the AP exam, they will give you choices. They'll say, you've got a burette, you've got a graduated cylinder, and you got a beaker. You would want to choose the burette to get the more accurate volume. So you would dispense your stock solution out of this. You put a little bit of water in here and then pour that measured amount into this volumetric flask. And then you're going to fill this the rest of the way up until the meniscus hits that etched line. The bottom of the meniscus hits the etched line. You're going to fill it up with water until that happens. And then you mix this up. And that's how you get an accurate volumetric measurement. One thing as a side note, you always, if you're diluting acid or base, you would want to add the acid or base into the water. So you would have the majority of this, you would have quite a bit of water in here already, and you would slowly pour in that acid or base into this. The thing is that when you're doing these acids and bases, they can be very exothermic, meaning that they're releasing a large amount of heat. In fact, for certain acids, when we dilute them, it's just the teacher, I'm the only one typically that does this, or a couple other chemistry teachers, but we will oftentimes do it in an ice bath because it actually generates so much heat that it can crack some of the glassware. And so we need, just to give you an idea of how hot this stuff gets, it's crazy. So to prevent issues with that, the other thing is that it can also generate because it's generating heat, it generates a lot of steam, and that steam is acidic and can really like choke you out. So you always want to make sure that you're doing this in a ventilated hood. I tried to do it the first year that I was teaching in the back storeroom, and it was all I could do to even get out of there without choking. So it can lead you to quite a bit of mess if you aren't very careful with this. But just make sure that you're doing this in a well ventilated area. The hood is the best place to do it in, and make sure that you're gloved up, gowned up, and got your eye protection on, because it can get kind of scary kind of fast. All right, so when we look at this, we look to see if it's going to be exothermic or endothermic. We will get into this more as we move into the year, but it's always good to kind of point this out. So when we're doing these, the solute particles are separated from one another. So remember, we were talking about the salt and how we're pulling the sodium and the chlorine ions off of that piece of salt. That is endothermic. So it's going to take energy to break those bonds. Okay. Then we are going to separate the solvent particles. So we're going to separate the water molecules from one another. We're not separating the hydrogen and oxygen off of them. We're separating the water molecules from one another and making room for these solute particles to fit in there. And then the solute and the solvent have to interact. So now they're going to come together, and that's exothermic. So bonds breaking and bonds making. So this is going to release energy. This is going to take energy. So the energy change is the overall process. It's the sum of those three things together. And that can be endothermic or exothermic. And we will learn about this, and we'll do math with it and everything as we move throughout the year. So here are some sample problems. Take a minute to pause the video and see if you can come up with the answers to them. All right, here's the answer to problem number 1. So pause and look over your answer. And then here is the answer to problem number 2, 3, and lastly, number 4. All right, so then we can look at some different ways that we can represent these solutions. And they really like these particle diagrams on the AP exam, so get used to kind of looking at these. And solutions represented by particulate diagrams where properties of the solution, such as concentration and particle or intermolecular interactions, can be illustrated. And they do this a lot. So if we look at these diagrams, we can see that we have HA as an acid, and it's represented here with our green and kind of maroon dots. Hydrogen is the ion with the green, and the acid is this maroon color. And then the water is this one. So let's see which one of these is more concentrated. Well, if these are our water molecules, you can see over here that we only have 2, 4, 6, 7 of them. Over here, we have 1, 2, 3, 4, 5, 6, 7. Oh, a whole lot more than 7, which is what we had over here. But it looks like our solutes here are all about the same amounts. So if this has less water and the same amount of solutes, and this one has more water and the same amount of solutes, then this one would be more concentrated, this one would be less concentrated. Here's another example where we've got, we looked at this one a while ago about how we're hydrating the anions and the cations. So this would be like a salt crystal, and they're pulling apart the positive and the negative ions here. And then we get into the idea of solubility. And we will pick up our discussion about that coming up on the next video.